Hi and welcome to the video lecture series on contact mechanics in the course M7033T, Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. This is the seventh part of the first video lecture on contact mechanics fundamentals, where we will learn about the Hertzian problem and its solution. In this video, we're going to go through the contact between ellipsoids in 3D or cylindrical bodies in 2D. Then we're going to look what the shape of the undeformed bodies and the gap between them has to do with the non-dimensionalization and the dimensionless groups associated with the gap. We're going to derive the set of Hertzian input parameters for the 3D problem. We're going to pay some attention to the dimensionless load and interference, and then we will discover the Hertzian universal solution, and then in the end there will be an exercise for you on the Hertzian problem in 2D. Hertz contact is the contact between two cylindrical bodies, well, at least in 1D. In 2D it's a contact between two spherical or two ellipsoidal bodies, and these are described then by some geometrical parameter. If they are cylinders, it's only one radii for each of the cylinder, R1 and R2 here, and then there are the material properties in terms of the Young's modulus and the Poisson ratio. Again, the contact between the two cylindrical bodies could be the contact between two asperities. In Hertz theory, the contact between the two cylindrical elastically deformable bodies has an equivalent contact model, and this is the contact between one elastic cylindrical body treated as a half space and another rigid half space. The geometry of that cylindrical body is now given by the reduced radius R, which is just the sum of the reciprocal radius of the two contacting bodies, and the elastic properties of it is given by E prime in this case. Well, we could have been using E star also if we like. Now, since one of the basic assumptions of this elastic half space contact mechanics is that the contact zone must be very far away from the contact boundaries, and so we realize that this cylinder at the vicinity of the contact, it can be described by a parabola instead. I mean, it's just the first interesting term in the Taylor expansion, and that parabola would then be x squared over 2r, where r is that reduced radius of the cylinder. And we can obtain an analytical solution in this case. And as I mentioned before, Hertzian theory can also be used to discover the contact between ellipsoids. One such case is the Hertzian, where we have G just composed by two contacting parabolas, and in this case this G defines another group that we can use to select our reference parameters in a clever way, so that we end up with an input parameter free contact mechanics problem. And this is exactly what Hertz did. It turns out that this group looks precisely like this. So it's the reference parameter for x squared divided by the reference parameter for the gap HR times the reduced radius r, and it can be found by scaling both G and X as we see here. So G is dimensionless G times HR, and X is dimensionless X times XR. And of course we can reformulate this and express it in terms of one-dimensional group here in green and a dimensionless expression for the parabolic gap. So if we now choose the first dimensional group to be 2 pi over 3 and the third dimensional group to be just 2 over pi squared, then we will have the Hertzian radius A, which cubed look like this, as a reference for the contact size or length, i.e. the reference parameters XR is equal to A. This can be seen by solving the first equation, the one for the first reference parameter set to 1, for HR, and solving the second one for PR. This gives expressions, gives those in terms of the reference parameter XR, such as we see here and here. And then when we have the expressions for HR and PR in terms of XR, then we can substitute this into the third equation for the third dimensionless parameter group to obtain XR cubed equal to 3WR over 4E star, which is precisely the Hertzian radius cubed. Okay, so we have seen that this choice renders the Hertzian radius A, but it also renders the Hertzian pressure, which is defined as the reference parameter for pressure, PR, and this is plainly accomplished by inserting XR equal to A into the equation for the second dimensionless parameter group and solving this one for PR. So now we have obtained the Hertzian pressure as a reference parameter for the pressure and the Hertzian radius as a reference parameter for the contact length or size. We have actually implicitly now seen what the dimensionless load, which we can call capital W for an Hertzian contact, is. The question is, can you figure that out yourselves? I guess you could, and the easy answer is that it's just 2 pi over 3, which actually means that it's half of the volume of a semi-sphere with radius 1. There is one more thing of interest here, and that's the interference. So we have seen that the maximum pressure, the Hertzian pressure, can be obtained directly from the input parameters, and we have also seen that we can estimate the Hertzian radius, the contact size, A. We would also like to know what the interference between the surfaces is. So the mutual approach which distance points in each body have seen as we loaded them against each other. Now this can be found by quite complex calculations, but these are summarized here. Of course, Hertz, he didn't, and in the book by K.L. Johnson, equation 341a does also give this, and it says that within the contact zone, where the deformed gap is 0, the deformation must be precisely this expression. By inserting the expression for the Hertzian pressure into this, we get the following expression, and by inserting the expression for the Hertzian radius into that one, we finally obtain a simplified expression for the deformation within the contact zone, and it looks like this. So it has, first part has to do with the Hertzian radius, and the second part is very similar to the parabolically shaped gap between the two surfaces. And this means that since the gap between the undeformed surfaces is exactly, well, the shape of the parabolic body, we have in the contact zone precisely this expression, which we can solve for the interference delta, and it's obvious that this just gives us delta is a squared over r, and finally we can obtain the dimensionless interference or rigid body movement or mutual approach as 1. So, in summary, we have a Hertzian non-dimensional 2D model because it's a dimension-reduced model due to the half-space assumption, but it is for the 3D contact between two parabolically shaped surfaces, or could be asperities, and it's given by the description presented here. So noteworthy is that we have our complementarity formulation, we have the expression for the dimensionless gap, deformed gap, we have the expression for the dimensionless deformation, and we have the expression for the dimensionless force balance. And we know that behind G there is now a parameter-free expression. Actually, it is precisely this expression. The Hertzian solution is actually a sort of a universal solution in that it based on a certain set of input parameters, E star, reduced radius, curvature, and load, gives every solution analytically, and the expression for the maximum pressure is the Hertzian pressure expression. We get the size of the contact from the Hertzian radius, and we also get the interference or the mutual approach between the two bodies. So all solutions given analytically, and we also know what the pressure distribution looks like. We know exactly what the deformation looks like within the contact zone. We know pretty much everything about this type of situation. One thing that has not yet been explicitly shown, and that's the expression for the reduced radius R in the case of two parabolic surfaces contacting each other. And it looks like this. Where R1 and R2 are the radii of the spheres for body 1 and 2 respectively. So the model for the Hertzian 2D contact, it looks pretty much the same as for the 3D contact. What really differs is the expression for the deformation, which here involves the logarithm of the distance between the point where the point load acts or where the pressure at a certain point acts and the point where we evaluate the deformation. And it is now up to you to derive the Hertzian non-dimensionalization in this case and express it then in terms of the Hertzian cylinder half radius B and the Hertzian pressure pH. And of course you should use the scaling from before to obtain your dimensionless variables X, H and P.